Welcome back, everybody. This is Earth and Space Science 102, and again, I'm your instructor for this class, Stephanie Welch. So today we're going to be continuing the topic of weather and climate, and we're going to talk about the global circulation of the Earth's atmosphere. Everything that we talked about in the very last video, the one where we talked mainly about air pressure and how temperature and humidity are going to be the controls of air pressure, that's going to be relevant to today's lecture. That's going to be relevant to what we talk about today. So air pressure is going to determine which way the air wants to move in the atmosphere. That's going to be the thing that actually creates moving air or wind in the first place. Because air is always going to want to move from high pressure to low pressure. Or another way of thinking about that is from colder, drier air masses to warmer, more humid air masses. So the very first thing that I want to start us off with today is a slide, a picture that you've actually seen before. And so this is going to be very important. It's a big sum up of how temperature and humidity will actually affect air pressure. So let's go into that now. First off, the drier and colder the air is, so the more lacking in water vapor and the lower the temperature, that means that the air molecules, the nitrogen and oxygen and all of that other stuff that makes up the air that we talked about in the last lecture, that is going to mean that those particles are going to be spaced more closely together. That means a denser air mass, plus having drier air means you have less water vapor, and the water vapor is the one component that's fairly light in the atmosphere. And so all of that means that you have a higher density and higher mass, air mass, that's going to be pushing down on the surface of the planet. That essentially means high pressure. And high pressure air always wants to, in a sense, sort of escape. You can kind of think about air in a balloon, helium air in a balloon, as being under very high pressure. When you pop the balloon, the air escapes. And so high pressure systems are all about having air moving out from a single point source. High pressure latitudes on the surface of the Earth are going to do the same thing. Air wants to diverge, air wants to move away. The warmer and more humid the air is, so wet, warm air masses, are going to be the opposite. The effect of the moisture in the atmosphere is going to be that you have that water molecule being less massive than all the other dry components in the atmosphere. That alone makes the air lighter and more liable to rise. Also, you have the effect of temperature, taking those individual particles and making them spaced a lot further apart. Because remember, they're moving a lot faster. They need a bigger personal space bubble. And so that means that those particles are going to be spaced further apart, and that means that you have a lower density, lower mass parcel of air, and that means that it's going to exert a lower pressure on the surface of the Earth. That means that that air mass wants to rise, and that more high pressure air is going to be moving in to replace it. And so the big sum up here is that high pressure systems are always associated with a divergence of air, pushing outwards of air on the Earth's surface. Low pressure systems are always going to be associated with a convergence of air, air moving into a point source on the surface of the Earth. So that's a little wrap up from last time, the effect of temperature and humidity on air mass, and it's absolutely crucial to understand that first before we get into anything else today. Another thing that I want to talk about that's going to be associated with this idea that air is always going to be moving across the surface of the Earth and in the upper atmosphere is the effect that gravity has. So when you think about the air that's part of the Earth's atmosphere, the only thing that actually constrains the air in the atmosphere to the Earth's surface is the effect of gravity. The effect of having planet Earth be this large, massive object in space that can actually control the destiny, can control this air surrounding the Earth and hold it to the surface of the planet. So if you just switched off Earth's gravity, if we could do that, then of course the air in our atmosphere would vacate the Earth. It would move outwards into space, because that's the ultimate transition from high pressure to low pressure. Air from the Earth's atmosphere would just be vented out into space. But we don't have that. We can't switch off Earth's gravity. We can't just make Earth suddenly less massive. And so what happens as a result is that the vertical variations in air pressure that do exist coast end up not being such a big deal because of the effect of gravity. You can kind of think of vertical variations in air pressure, the idea that the Earth's atmosphere is thinner in the upper part of the atmosphere, as counterbalanced by the effect of gravity. So air pressure is pushing outwards away from the surface of the planet, and gravity is pulling that air back in. And our atmosphere is the effect of the balance between those two forces. So it's a little bit of an oversimplification, but for the purposes of this class, let's just assume that we don't have to deal with vertical differences in air pressure. It's going to mainly be horizontal differences in air pressure that are going to create the global circulation of the Earth's atmosphere. Now, when we do that, when we look at one point on the surface of the Earth and compare it to a different point on the Earth's surface and see that there is some discrepancy in air pressure, sometimes that's not a real thing that's going to create winds, because we might be talking about two different elevations. So to be able to compare and contrast and look at how air is going to move across the surface of the Earth, we first have to do this thing where we're going to correct for elevation, correct for the effect of the change in altitude and the effect that that has on air pressure. So we have to change everything from the get-go into standard sea level air pressure. We have to correct for anything that's above air pressure, above sea level. So let's say, for instance, we were comparing the air pressure in New Orleans, Louisiana, which is, for our purposes, let's say at sea level, and Denver at Mile High Stadium. You'd first have to correct for elevation before you could make any assumptions about whether air was going to move from Denver to New Orleans or New Orleans to Denver. So let's figure out how that works first. The main thing that I want to you to take away from this is that you do have to correct for elevation, and not necessarily technically how it's done. So if you look at all of the points on the diagram on this page, you can see we have point A, B, C, and D, and you have very different elevations at all of these individual points. Point A is 600 meters above sea level, point B is 300 meters above sea level, point C is 1100 meters above sea level, and point D, let's assume, is at sea level. So what we want to do is we want to correct for elevation and bring all of those down so that we're looking at sea level air pressure. Then once we do that, we can figure out where the air is moving from and to, and what the wind directions are going to look like as a result. So what actually happens is that with every 100 meters of change in elevation, you have to add 10 millibars of air pressure in order for that to essentially be a real reading. That's how you correct for elevation. And so once you do that, and that's all done for you in this diagram, you're comparing apples to apples instead of apples to oranges. And when you do that, you get an idea of where the actual high pressure and where the low pressure really exists. So even though it doesn't look like it in the first diagram up on the top, it looks like the highest elevation has the lowest air pressure. When you correct for your change in elevation, it turns out that air would want to move from point A all the way over to point D. And the reason for that is because it's moving from comparatively higher air pressure at 1,012 millibars over to the lower air pressure at 1,000 millibars. And then once you do that, you get a real version of how the wind wants to move and how air wants to move across the surface, always going from high to low pressure. So it's going to be horizontal differences in air pressure and not vertical differences in air pressure that really equate to wind on the surface of the Earth. The only reason why the wind blows in a hurricane is because you have a very, very low center of pressure at the eye of that hurricane, and air moves inward as a result. The only reason why we might have winds coming out of the northeast today is because that direction is going to be where the high pressure air is, and it's moving towards the low pressure. And so it's variations in air pressure across the surface of the Earth corrected for elevation that actually equate to wind. Before we get into the other things that are going to control the global circulation of the atmosphere and then cause the deflection of that wind, let's look at just a simple example of a pressure-driven wind that's actually applicable to us in South Louisiana, or really anywhere across the Gulf Coast. One thing that always happens, let's say if you go out to the beach and you go maybe, let's say, camping outside of Pensacola and you're near the beach. one thing that is going to happen in these kind of environments is that you get this reversal of wind direction between the daytime highs and the nighttime low temperatures. And the reason why this happens is because of the unequal way that the land mass is heated relative to how the water is heated. The takeaway message from all of this is going to be that it takes a lot more time and energy to heat up water than it does to heat up the land. So let's assume that it might take 2 to 3 times as long to heat up water as it does to actually heat up the land mass. Think about the difference in the time it takes to boil water versus the time it takes to fry an egg. And that gives you kind of an idea, the egg being analogous to heating up the land mass and the boiling of the water being analogous to heating up the oceans. You get kind of an idea of the difference in time it takes to heat up land versus ocean. Okay, because of this, you get this reversal of wind direction between daytime and nighttime, and this is called a sea breeze and a land breeze. So I want to go into this a little bit. The daytime temperature controls are going to be that the land is going to be warmer than the water in the ocean because the surface of the land, let's say the sand at the beach and the grasses on the dunes and the land surface itself, is going to heat up pretty rapidly. Then that means the air above it is going to be comparatively warmer than the air above the water in the oceans. So because you have colder temperatures over the water and warmer temperatures over the land, then your basic pressure difference is going to be high pressure over the oceans, low pressure over the land, and air always wants to move from high to low pressure. And so that's exactly what it does. Air moves from high to low pressure onto the land, converges on the land, that low pressure air rises in the atmosphere, and you get storms because you have clouds forming, maybe late in the afternoon. That's your very, very typical sea breeze. So the reversal of this happens at night because just as the land heats up really rapidly, at night it cools down rapidly. And that means you get the reversal in temperatures. Whereas in the middle of the day, you had warmer temperatures over the land, at night you have warmer temperatures over the ocean and colder temperatures over the land. And so then air moves from high to low pressure from over the land to over the oceans. And you get a land breeze, a breeze that's coming from the land as opposed to the sea breeze during the day that's coming off of the water. So either way you look at it, it's just exactly a pressure-driven wind, and essentially nothing else is controlling or deflecting that moving air. It's air moving from cold to hot, from high to low pressure, always. So the global circulation of the atmosphere is a little bit more complicated than that, but the first and foremost control on this is still going to be that air moves because of differences in air pressure, always from high to low. Before we get into that, I want to give you a way of looking at differences in air pressure across a map that's going to be a little bit more simple than looking at, let's say, 1,000 individual little points with a number next to it. When any scientist is given a large amount of data to work with, especially data that's spatial, data across, let's say a map of Louisiana or a map of the United States, the first thing that they're going to do, whether that data might be elevation or temperature or air pressure, is to contour that data, to feed all of that information into a computer and have it spit out lines. And each one of those lines means that along that line you have an equal elevation or an equal temperature, an equal air pressure. When you're doing this for elevation, let's say you're contouring elevation in the Rocky Mountains, what you would end up with is what geologists use, which are topographic maps. And a topographic map will show you where the peaks and where the valleys are. And it's going to be lines connecting equal elevation that show you where your relative elevation change is. It's always going to be across those lines. If you're doing the same thing with something that's a little bit more abstract than elevation, if you're doing the same thing for, let's say, air pressure, then what you create is what meteorologists use, which is an isobar map. So if you break down the word isobar, iso, like isosceles triangle, has 2 equal sides. Iso means equal, and bar, bar, means pressure. And so isobar is equal pressure, lines of equal pressure, just like those lines of elevation on a topographic map. And so the lines that get generated mainly by computers, but it is possible to contour by hand, those lines of equal pressure are going to tell you where similar places are, let's say across the United States, like in this picture, where you have some equal pressure along those lines. It means as you cross those isobars, you're either increasing or decreasing in pressure. Now, one thing that makes this a little bit easier to read is that you actually have the H's and the L's. The H's are the high pressure and the L's are the low pressure across this map. Once you've contoured it, you can take all those data points away and you get a much cleaner map to look at. So whereas before you had a million little point sources on a map and you were trying to figure out where the highest number and where the lowest number was, the finished product shows you just where the high and the low pressure exists. And once you know that, you know which direction the wind moves, always from high to low. Just like water running downhill from high elevation to low elevation, this is air pressure moving from high pressure to low pressure in the atmosphere. And remember that that pressure is predominantly controlled by temperature and humidity. So it's moving from cold and dry to warm and humid. So the next thing that we're going to get into is going to be the global circulation of the Earth's atmosphere. And what I like to do with this is to talk about each of these forces in turn that either creates the winds or causes deflection of that moving air across the surface of the planet. Then once we get that force sort of understood and get that under our belt, then move on to talking about how that affects the entire global perspective, the global circulation of the Earth's atmosphere. Now, the most important is going to be one that we essentially know already. It's just going to be by a less common name. We call the thing that actually creates winds across the surface of the Earth the pressure gradient force. And all this really means is what we've been talking about all along. Air always wants to move from high to low pressure. It doesn't matter if you're north of the equator or south of the equator. It doesn't matter which hemisphere you're in. It doesn't matter if you're on Earth or outer space. Air always wants to move from high to low pressure. The pressure gradient force basically takes that concept and specifies it a little bit more. Not only does air want to move from high pressure to low pressure, the greater the difference in pressure over a smaller distance, the faster the wind will actually want to move. To remember the effect of this, just think about a really strong, very small hurricane. You can generate amazingly high winds in excess of 155 miles per hour in a Category 5 hurricane. And the only reason why that's possible is because the difference in pressure from the outside of the storm to the inside of the storm is very, very great. It's a huge difference in air pressure acting over a small distance, which means pressure gradient, or essentially sort of the slope in pressure, the rise over run, is a very large difference in air pressure acting over a short distance. So this is a gradient like any other slope. You have a rise and a run. And the rise in this case is differences in air pressure, and the run of that slope is going to be a distance across a map. If you're talking about a really large change in pressure across a very wide distance, like the change in pressure that happens on the surface of the Earth as you go from, let's say, the North Pole to the equator, then it doesn't equate to really fast wind speeds because that's a large pressure gradient acting over a huge distance. So the larger the difference in pressure, the faster the air moves, as long as that's over a short distance. That's what a pressure gradient force, or PGF, is all about. Now, to kind of cement this before we go on to how this affects the global circulation of the atmosphere, I want to go through and calculate a pressure gradient, given a very simple example. From one line to the next, from one isobar to the next, you have a change in pressure in this picture from 1,020 millibars of air pressure at point 1 to 1,016 millibars of air pressure at point 2. That means there's a difference in air pressure from point 1 to point 2 of 4 millibars. And that's 4 millibars of air pressure difference acting over 100 kilometers, or something like 60 miles, if you prefer to work in miles. So that means that is the pressure gradient, 4 millibars over 100 kilometers. And in reality, if you're comparing this to wind speeds in a hurricane, something like this wouldn't equate to very, very fast wind speeds at all. It takes a much sharper change in pressure over a shorter distance in order to equate to really fast wind speeds. We're not going to take in this sort of this far in this particular class, but if you really wanted to, you could then work out the wind speed based on how much of a change in pressure has occurred over that short of a distance. So the wind speed is going to be determined by the pressure gradient force, as is the direction the wind moves. This really is the most crucial force and the one that controls which direction the air wants to move, at least initially. And so now this is the part where we're going to get into our simplest model of the global circulation of the Earth's atmosphere. If we made a huge number of assumptions, if we took the Earth and instead of allowing it to continue spinning, to continue rotating, if we just were able to sort of just hold it still for a minute. So Earth was suddenly not spinning. And we also had to make a couple other assumptions. If we took Earth and in addition to not allowing it to spin anymore, we had it as a perfectly smooth sphere, like a marble or a basketball. Then we would be able to tell which direction the air would want to move, because the only control on the global circulation of the atmosphere would be the pressure gradient force. The only thing that would be causing the atmosphere to be moving at all is the unequal heating of the Earth's surface. So this is going to take us to the next idea, the global perspective. Because the Earth's surface is heated more along the equator and the surrounding regions, and of course that's seasonally dependent, but because the central part of the Earth around the equator up to the Tropic of Cancer and down to the Tropic of Capricorn, those are the only parts of the Earth that receive directed overhead sun for a longer period of time. Those are going to be the warmer parts of the Earth. The colder parts of the Earth, obviously, are going to be closer up to the poles where you have less directed sunlight. And that unequal heating of the surface of the Earth is going to set up the primary thing that controls winds. Air wants to essentially originate from where it's cold, where the pressure is high, up at the poles, and then move down to the equator. Once the air meets at the equator, originating from the two poles, then the air moves up into the upper atmosphere, forms storms, and then that air then moves back to the poles again. And so in comparison to the complications that are going to follow, this is a really, really massively oversimplistic version of the circulation of the Earth's atmosphere. But it already explains some things that we already know. The basic distribution of heat across the surface of the Earth is obviously due to the unequal heating of the Earth's surface. The warmer temperatures near the equators, the colder temperatures near the poles. And air moving from where it's cold at the poles down to the equator where it's warm, that's going to show you where the tropics are going to exist, where you have tropical rainforests, where you get a lot of precipitation. It's going to be around the equator. And the world's ultimate desert is where you have the highest pressure, and that's actually going to be up at the poles. So we don't really think of the Arctic Ocean and Antarctica as deserts, but they really are. They have the lowest amounts of precipitation anywhere in the world, and that's because of the unequal heating of the Earth's surface and high pressure near the poles and low pressure near the equator. Now, this is the simple model. This is overly simplistic. But in order to understand all of the complexities that we're going to introduce a little bit later on, you have to first understand this. So the next thing that we're going to talk about is the Coriolis force. We're going to talk about the Coriolis force first, and then we're going to apply it to the global circulation of the Earth's atmosphere. So first off, the Coriolis force is our sort of fancy name given to the idea that because the Earth is rotating, anything moving across the surface of the Earth is going to be affected by this apparent deflection. So it's essentially going to be different depending on which hemisphere you're in. If you're north of the equator in the northern hemisphere or south of the equator in the southern hemisphere. It's essentially going to be a complexity that arises in ocean currents and the global circulation of the atmosphere, in anything where you have something moving across the surface of the Earth, if enough time has elapsed that the Earth is actually spinning out from under that thing as it's moving. So you always hear the Coriolis force described as the reason why water might circulate a different way down a bathtub drain or circulate a different way down a toilet, depending on which hemisphere you're in. That is too small of a feature for the Coriolis force to be the thing that's going to actually affect the circulation. Essentially, if you have exactly the same sink 20 degrees north of the equator or 20 degrees south of the equator, then the circulation of water down that sink is not actually going to be affected by the Coriolis force at all. The thing I like to tell people most of the time is that if you had, like, let's say, a toilet the size of Texas, then the circulation of water and everything else down that toilet is going to be determined by the Coriolis force, because enough time will have elapsed when you're thinking about whatever it is that's moving towards the very center of that drain. If it's a low pressure system, for instance, if it's something like a hurricane, then by the time the air moves from outside that hurricane down into the very center of it, as the air is moving across the surface of the Earth, enough time has elapsed that you'll have a deflection. And in the northern hemisphere, that deflection is always going to be to the right. So another way of thinking about the Coriolis force is going to be that this is going to be a force that is going to increase in intensity as you move away from the equator and up towards the poles. So if you were, let's say, standing on the North Pole, if you were Santa Claus in his sled, and you were going to go down to some point on the equator, let's say Colombia in South America, and you were traveling across the Earth's surface, what would happen would be, if you didn't account for this in your trajectory, if you were Santa Claus and you didn't know any better and you didn't know about the Coriolis force, then what would happen is that you'd actually end up off in the Pacific Ocean. Because let's say if it took 6 hours to complete that journey, then the Earth would have rotated out from under you, basically undergone a quarter turn to the east as you were traveling across the surface. And so Santa Claus, instead of arriving in Colombia, would arrive off into the Pacific Ocean. So there are lots of individual examples for the Coriolis force, but basically what this is going to mean is, because the Earth is spinning, it's spinning to the east, this is the direction of the Earth's spin, then anything moving in the northern hemisphere that's large enough is going to have a deflection to the right, and anything moving in the southern hemisphere is going to have a deflection to the left. Now, as far as the global perspective of all of this is going to mean that our very, very simple model, where we had high pressure air near the poles and low pressure air near the equator, is going to be a little bit more complicated. It means that air moving from the poles to the equator is going to heat up and get deflected off to the right. Air moving from, let's say, the South Pole up towards the equator is going to warm up and it's going to get deflected off into the left. And so what's going to happen as a result of all of this is that we just have a much more complicated model to work with. First off, the first complexity that's going to arise is that instead of having one cell of convection, one big rotating column of air in each hemisphere, we're actually going to have 3 cells of convection per hemisphere. So air moving, let's start from the North Pole, for instance. Air moving from the North Pole down to 60 degrees will warm up, and as it warms up, it's going to uplift and move up into the upper atmosphere and cycle back around to the North Pole again. So that's one cell of convection from 90 degrees north, the North Pole, down to 60 degrees latitude. And these latitudes are east-west lines across the Earth's surface that are going to measure your north-south direction, going from 0 degrees at the equator to 90 degrees at the poles. So that's one cell of convection already that we have, going from the pole to 60 degrees and then back around again, one cell. The next one that's going to develop is going to go from 30 degrees down to the equator. So you have high pressure at 30 degrees, and that air moves from 30 degrees down to the equator, turns back around again in the upper atmosphere, and then comes back again. So that's the second cell of convection. And because you have those air masses moving in the opposite directions in that first cell of convection up between the pole and 60 degrees, and that second cell of convection between the equator and 30 degrees, that sets up a third cell of convection from 30 to 60 degrees. So that's 3 cells of convection, and everything that's going on in the northern hemisphere is mirrored by what's going on in the southern hemisphere. Now, when I say that it's mirrored, it means that it's not actually going to be exactly the same. It's going to be like your reflection as you look in a mirror, and everything is going to be exactly the same but opposite. Because the Coriolis deflection in the southern hemisphere is going to be off to the left, that means that everything essentially in the southern hemisphere is actually going to be the mirror image of everything going on in the northern hemisphere. So the next thing we're going to talk about, beyond just these things called the Hadley cells, these 3 cells of convection per hemisphere, is going to be which way the air moves across the surface of the Earth. Now, again, let's start off at the pole, at 90 degrees north. If that air is moving from the North Pole down towards the equator, if the Earth were not rotating, it would continue to move until it reached the equator. But that's not what's happening. The Earth is rotating, and instead of moving in a straight line from the North Pole down to the equator, the air is diverted off to the right. And right from that perspective is going to actually be west. That air is going to be moving to the west. So you have to think about it like wherever the start of that arrow is, wherever you're starting off. If you're Santa Claus standing on the North Pole, or someone trying to take off in a helicopter at the North Pole, whatever it is, then you have to remember that along the way, you're going to get deflected off to the right, not because you're actually moving off to the right, but because the Earth is rotating out from under you. So these winds between 60 and 90 degrees north are called the polar easterlies. Prevailing winds are always named for the direction they're coming from and not moving to. So even though they're moving to the west, they're coming from the east, which is why we call them an easterly, a polar easterly, because you're between 60 and 90 degrees. The next of these prevailing winds that are going to be established is going to be between 30 and 60 degrees. So 60 degrees is a low pressure belt, 30 degrees is another high pressure belt like the poles. So at 30 degrees, you have a divergence of air. Air moves away from 30 degrees and back down towards the equator, and then up to the 60 degrees. So what happens as a result of this is that air moving from 30 to 60 degrees is going to want to move in a straight line again, but be deflected off to the right. The right this time is essentially the mirror image of the right in 60 to 90 degrees, because you have, again, the Coriolis deflection occurring to the right in the northern hemisphere. So that means that you have set up a prevailing wind that originates from the west and moves west to east. So we call it a westerly. That's going to be the prevailing winds between 30 and 60 degrees. And that's essentially why cold fronts always come from the west. It's because the cold fronts are part of bigger low pressure centers that are going to develop in the west and move in accordance with the westerlies. The final one of these prevailing winds that we're going to talk about in the northern hemisphere is going to originate again at 30 degrees at that high pressure belt and move from 30 degrees down to the equator. The area right around the equator is called the ITCZ, or Intertropical Convergence Zone, because that's the ultimate low pressure belt. That's the ultimate low pressure on Earth, the warmest part of the Earth. And so the air coming from 30 degrees north and 30 degrees south is going to converge at the equator, at the ITCZ. And so we call that wind that's coming from the east, the prevailing wind between the equator and 30 degrees, a trade wind. not because it's following our originally established scheme where we would call it an easterly again, but because these are the winds that blew the great ships of exploration hundreds of years ago across the Atlantic Ocean. So the trade winds blew the old trade ships around. So between 0 and 30 degrees north and 0 and 30 degrees south, you have air coming from 30 degrees north and south, the high pressure, converging in on the equator, and then after it's converged in on the equator, flowing along the equator itself and slowing and stilling. And so you don't really have a very fast moving wind right along the equator itself. Things sort of slow down. The prevailing winds are sometimes referred to as the doldrums, sort of a lack of a prevailing wind because things slow down right along the equator. So again, a reminder, just like with the Hadley cells, everything that's going on with the surface motion of air is going to be mirrored in the southern hemisphere relative to the northern hemisphere. It's not going to be an exact copy. It's going to be a mirror image because the Coriolis deflection is going to be to the left in the southern hemisphere and to the right in the northern hemisphere. Okay, so when you take in all of this as a whole, this is a really complicated idea. And it's made even more complicated by the fact that you have to think about where the air is coming from and where the air is moving to. But at least that part's a little bit more simple. Air is always coming from high pressure and towards the low pressure. High pressure is going to exist at 90 degrees and 30 degrees north and south of the equator. Low pressure is going to exist, so a convergence of air, at 60 degrees north and south of the equator and at the equator itself. All of that, where the high pressure and low pressure exist, is going to control where the air is moving from and where the air is moving to. The Coriolis deflection is going to control which way that air wants to move within each of those latitude belts. And that's 0 to 30, 30 to 60, and 60 to 90 degrees north and south of the equator. So another thing that makes all of this complicated is this is still a much more accurate picture of what happens with global atmospheric circulation, but it still doesn't take into account all of the complexities. I like to think about this as the model of Earth, where Earth was a huge rotating basketball or a huge rotating perfect sphere. This is essentially what atmospheric circulation would actually look like on Jupiter. Jupiter being a lot more like a perfect sphere, a sphere mainly made of gas, means that you don't have the kind of seasonal variations in air pressure that we have on Earth, and the kind of variations in air pressure that occur because parts of the Earth's surface are covered in water and parts of the Earth's surface are covered in continents. So let's talk about how precipitation is going to be affected by these idealized pressure belts. Essentially, where on Earth you have deserts are going to be where you have high pressure, and that's going to be at the poles at 90 degrees north and 90 degrees south. The polar latitudes around 90 degrees are essentially going to be a perfect desert, as are the 30 degrees. The 30 degree is going to be a little bit more complicated, and I'll get back into that in a minute. So essentially most of the world's deserts, the Sahara Desert, the southwest of the United States, most of South Africa, are all going to be either around 30 degrees latitude, north and south of the equator, and closer up to the poles. Where you get a lot of rainfall is going to be where the air converges on the surface of the Earth, and that's where you're going to have low pressure. That's going to be around 60 degrees north and south, and at the equator. That's going to be where most of the air wants to converge. Okay, so this is a really nice picture here of these sort of idealized pressure belts where the air is converging and diverging, moving up into the upper atmosphere or coming down from the upper atmosphere. You can see your polar highs as your ultimate desert, where the air is moving away, and your other desert being 30 degrees north and south of the equator. At 60 degrees north and south of the equator, you see all of your cloud formation because you have air converging there. And the same thing's going to be true at the equator. Your world's tropical rainforests that thrive under those rainy conditions, those are all going to be along the equator itself. Now, to take us into this final complexity and the third and final thing that's going to create and deflect air moving in the Earth's atmosphere, I want to first show you one thing that is not going to be the result of these perfect pressure belts, and it's going to give you a little taste of what's to come. Our location, our latitude here in South Louisiana is approximately 30 degrees north of the equator. If you take the latitude at the Causeway Bridge as you enter into the city of New Orleans, or at that point you'd actually be in Metairie, but the foot of the Causeway Bridge on the south side, that's exactly 30 degrees north latitude. According to everything that we've talked about so far, 30 degrees north latitude is supposed to be a desert. It's supposed to be where air diverges across the surface. It's certainly where some deserts of the world do actually form, like the Sahara Desert, but nobody in their right mind could describe South Louisiana as a desert. So even though we're supposed to sort of be in a desert right here, we're supposed to be at this huge high pressure belt right here at 30 degrees north latitude, we have a very rainy climate, almost a practically tropical climate. And that's because of this last complexity. Because essentially we're coastal, and because of the effect of low pressure systems coming in off the Gulf of Mexico, we have a more complicated dynamic of what goes on with our weather just around here. It takes into account this third and final complexity. I like to kind of sum this up as the effect of friction and the effect of having a non-uniform surface to Earth. Something that would have a uniform surface would be more like Mars. Mars doesn't have any standing surface water to speak of, and so you don't have to worry on Mars about the effect of heating up the landmass quicker or slower than you heat up the oceans, because the entire surface of the planet is uniform. You would still on Mars have to deal with the effect of friction, because there are changes in elevation across the surface of that planet, as there are changes in elevation across the surface of the Earth. So friction is going to deflect moving air. It's going to slow down moving air moving across the surface of the Earth. Trees are going to slow down air. Mountains are obviously going to slow down air. Any discrepancy away from sea level is going to take moving air moving across the surface of the Earth and slow it down and deflect it. The effect of having a non-uniform surface is going to be that even though we should sort of almost have these idealized pressure belts, we have something that is less like those idealized pressure belts, because you have seasonal variations in climate and because you have the slower rate in which water heats on the surface of the Earth in the oceans versus the rate in which the land surfaces heat up and cool down. So when you take all of this into account, we can't really go piece by piece and draw out global circulation of the Earth's atmosphere. We basically have to look at a map of what it looks like, what the semi-permanent high and low pressure zones are, and they're not going to be these perfect belts that move across latitudes. They're going to be individual centers of low and high pressure that are affected by changes in season. So the first picture I want to show you of this is what conditions look like, what the general idealized circulation of the Earth's atmosphere looks like in the month of January, which is winter in the Northern Hemisphere. So in winter in the Northern Hemisphere, that means that you have the most concentration of sunlight occurring in the Southern Hemisphere at the Tropic of Capricorn. So in the Northern Hemisphere, this means that you're going to have these centers of low and high pressure that don't exactly mimic where those lines of low and high pressure existed on the idealized pressure map. So let's try to find maybe a little bit of this idealized centers of low and high pressure across this map. If you look up at the poles at 90 degrees at the very top of the map, then you're supposed to have high pressure, and you do in a sense still. You do have dry, arid conditions in a sense, but very cold conditions, so high pressure existing year-long up at the poles. At around 60 degrees north, you still do have these low pressure systems, but they become less a part of the inner part of continents and more something that's going to control air pressure over the oceans. You have the Aleutian high and the Icelandic low. And so those low pressure systems are going to be what remains of those idealized pressure belts. Same thing at 30 degrees here. You're supposed to have highs, and you do still have highs. You have the Pacific high, the Bermuda high, still at 30 degrees. Then you have your ultimate low pressure belt along the equator, the intertropical convergence zone that connects low to low to low, or L to L to L on the map. Then in the southern hemisphere, at 30 degrees, particularly in the oceans, you have high pressure and lower pressure at 60 degrees south, higher pressure near the poles. So it's messy. That's the thing to take away from this. It's definitely a little bit more complicated than it would have been if the Earth's surface were entirely covered in water or entirely covered in land. Let's now take a look at how this is going to change from winter in the northern hemisphere to summer in the northern hemisphere. So we go from January to July. And in July, things in the southern and things in the northern hemisphere look a little bit different. The effect of this Bermuda high in the middle of the Atlantic at 30 degrees north, it becomes a little bit larger of an influence. You still have the Pacific high, but it moves up a little bit. You still have the Icelandic low, but it also moves north a little bit. You still have that low pressure system, the ITCZ, that red line, nearly at the equator, but not perfectly at the equator. You still have highs at 30 degrees south. And so it's just a little bit more messy, it's a little bit more complicated, but that's the reality of the world that we actually live in. We don't have these idealized pressure belts, but we can still somewhat feel the effects of those pressure belts in the deserts that develop at 30 degrees north and south of the equator, and the tropics at the equator itself. Even though here in Louisiana, according to those idealized pressure belts, we're supposed to live in a desert, instead we live in a very humid, very warm environment. So much of the global circulation of the atmosphere is going to play a really, really big role in how hurricanes move, how upper level lows move. And so everything that we learn today, particularly as you go back and you try to equate all of that with those prevailing winds, those are going to be the steering currents for smaller, more ephemeral centers of low and high pressure. And they are going to play a huge role in our day-to-day weather. So that's essentially what we're going to talk about next time. We're going to talk about these things called mid-latitude cyclones, referred to by weathercasters as being upper-level lows. And we're going to look at the effect that those have on our weather here, specifically in South Louisiana, and the weather across the United States. And then we'll go on to do the same thing with tropical systems, tropical low-pressure systems like hurricanes and tropical storms. So that's all we have time for today. Until next time, keep looking up.